be good afternoon or whenever this is. Alright, so we're going to commence thesis of organic chemistry today. So CHM 001 organic chemistry. So we're going to be doing the introduction or introductory class to organic chemistry. Okay, so I believe you have heard of this organic chemistry before now. Alright, so look at the word itself. When you see organic, the word organic naturally or ordinarily means something that is natural or naturally occurring. For instance, if somebody says that I have maybe somebody is talking about their online followership, for instance, Twitter followership or Instagram followership, they can say, okay, I have maybe they say I have 900,000 organic followers. Organic means natural, like the people they were actual people that followed them. Okay, not like the bots, the followers, or maybe they did some follow train and they were able to gather 900,000 followers at the end of the day. Okay, so organic simply means naturally occurring, basically. So when you hear the word organic chemistry, it means we are dealing with chemistry of naturally occurring matter. That means we are dealing with naturally occurring compounds. We want to study naturally occurring compounds. Okay, so we say that organic chemistry is an aspect of chemistry that deals with the study of naturally occurring matter. Okay, so in this case now that is just some non-specific. Now that definition is not quite specific. Okay, so as we move on, you get to see what we mean by what the specific definition is or should be. So in the case of organic chemistry, basically that means we'll be dealing with or will be concerned with the structure, we'll be concerned with the structure. Basically we'll be concerned with the composition. That is, what are those elements contained in organic matter or organic compounds, or let's say naturally occurring substances. Okay, so we'll be concerned with the composition, be concerned with the properties, we'll be concerned with the production, that is the different organic reactions, how the organic compound or how different organic compounds actually react to form another organic compound, or how some non or inorganic elements or compounds actually react to form organic compounds, and so on. Alright, so we also talk about the uses and effects of organic compounds. So we also talk about uses and effects. So how can you produce organic compounds? What is the composition? Okay, and that is closely related to the structure. Of course, we talk about composition, that is the elements or the components, okay, that make up the organic compound. And we also talk about structure, that is how the elements or the different components are related. All right, so those are the things we'll be looking at in this topic. It's actually a very broad topic, so but of course at this level you just need to know a few basic things about this organic chemistry, so those are the things we'll be looking at. So you'll be surprised that despite the fact that I said they are basic things, it's still going to take a lot of time to actually master all the basic things, so to speak, that we need to master under this topic. Alright, now so to get very specific, I just said now that organic chemistry deals with the study of organic matter. That is, we'll be looking at the composition, the properties, production, and uses and effects of organic substances. That is naturally occurring substances. Now, to be very specific, we'll say that organic compounds are compounds of carbon. Okay, so organic compounds are compounds of carbon. So we see that organic compounds are compounds of carbon. Compounds of carbon. That is compounds that contain carbon. Now that is not correct. We'll stop here because a lot of compounds contain carbon. Okay, like CO2. That does not mean CO2 is organic compound in this classification. Alright, so that our study here. Alright, so we get more specific. We say organic compounds are compounds of carbon with the exception of so these are the exceptions. The following are exempted: CO2, that's the oxides. Okay, so generally I can say the oxides with the exceptions of oxides. I mean oxides like your CO2, that's carbon 4 oxide, and CO, which is carbon 2 oxide. These ones are exempted. That is, we're generally talking about organic compound. When we talk about organic compound, we say they are compounds of carbon, but these are not organic compounds, despite being compounds of carbon. Alright, so that means not all compounds of carbon are organic compounds, but all organic compounds are compounds of carbon. That is, all organic compounds contain carbon, but not all substances containing carbon are organic compounds. So what are those substances that contain carbon that are not organic compounds? So those are the ones we are looking at. These are the exceptions. Okay, so oxides. Now these are the oxides we're talking about. Then we can also have carbonates. Okay, we also have what we call the hydrogen carbonates. I'm going to give you examples. So the hydrogen carbonates are also not organic compounds, despite being compounds of carbon. Okay, and then we have what we call the carbides. Okay, so examples. We have given example of, so an example of carbonate is this magnesium carbonate. Okay, you can also have the hydrogen carbonate, H2CO3. These are not organic compounds. This what do you call this now? Trioxocarbonate acid rather. This is trioxocarbonate acid. Alright, so hydrogen carbonate, that is compound that contain these two. For instance, you can have this calcium hydrogen carbonate. Alright, so you can have this. Okay, the IUPAC nomenclature. Alright, don't mind the way I'm pronouncing them now. Okay, so this is carbides. You can have what we call calcium carbide. You can have magnesium carbide. Okay, so whenever you see substances like this, are what we call carbides. Alright, okay, so when you see substances or compounds like this, they are not organic compounds. Okay, but other compounds which we'll be looking at are organic compounds. Alright, so that's the definition specifically. Organic compounds are compounds of carbon with the exception of oxides such as carbon 4 oxide and carbon 2 oxide, carbonates, e.g. magnesium carbonate, hydrogen carbonates, e.g. calcium hydrogen carbonate, and carbides, e.g. calcium carbide, magnesium carbide. Alright, so apart from this set of carbon compounds, okay, of every other compounds of carbon that we're going to be looking at, okay, as we will see as in this topic as we proceed, they are organic compounds. So they qualify to be classified as organic compounds. Alright, so that is that about that. So we say that organic compounds contain carbon as the major elements. Okay, so that is why we call it that's why we say they are compounds of carbon. Alright, so they contain carbon as the major element. So they can also contain other, of course, carbon would not sit alone or stand alone in the compound. So they also contain other elements, and these other elements that you're going to be seeing in organic compounds, okay, that actually form some sort of bond with carbon atoms. Okay, you're going to be seeing stuff like hydrogen, you're going to be seeing oxygen, you're going to see sulfur, You're going to see silicon, nitrogen, phosphorus, and the halogens. By halogens, I think you should still remember that from the introductory chemistry. You should still remember halogens. Talk about the fluorine, the chlorine, the bromine, and iodine. All right, so that's what I mean by the halogens. So you're going to be seeing, elements like this combined with carbon. Okay, in the organic compounds we're going to be looking at. All right, so when so I said that in organic compounds you're going to be seeing carbon. Okay, so in different bonds with substances like with elements like hydrogen, oxygen, sulfur, nitrogen. You're going to be seeing it with nitrogen, phosphorus, and the halogens. Okay, we talk about what halogens are. Group 7 elements. So we're going to have what is it now? Fluorine, chlorine, bromine, iodine, etc. Fluorine, chlorine, bromine, and iodine. All right. So is it iodine? Okay, iodine. Okay, whatever you call it. All right. It should be noted that organic compounds contain I mean those that contain carbon and hydrogen only. Okay, they are specially called hydrocarbons. So when you hear hydrocarbon, it means it contains carbon and hydrogen only. Okay, so hydrocarbons contain carbon and hydrogen only. All right, so you see they contain carbon and hydrogen only, so that's why they are called hydrocarbons. All right, so these are like the commonest organic compounds you're going to be coming across in in our studies as we move on. All right, so they are called hydrocarbons. Please bear that in mind. You may be given a question where, of course, they may not ask you this directly, but most times you'll be given a question where the only way out or the way to actually solve the problem properly is to understand this simple fact that organic compounds or the hydrocarbons generally are actually organic compounds that contain only hydrogen and oxygen. I mean, there are problems where if you don't know that, you will not even be able to make a headway. All right, so that is that about that. So we said organic compounds are compounds of carbon. That is, carbon is the major element in organic compounds. So then the question should come to your mind. The question should be that why is it carbon? What is so special about carbon, or that makes it the major element in organic compounds? So there are some properties of carbon that actually make it a fit that makes it so, or there are properties of carbon that make it so special. That is, there are some characteristics that carbon possesses that makes it so special. All right, so we're going to be looking at those properties one after the other. Okay, so they are called the unique properties. Okay, for the purpose of this class, we will call them the unique properties of carbon. We look at them one after the other. Unique properties of carbon. Okay, so we take them one after the other. All right, so the number one of them which we'll be looking at is excitation. The next one we'll be looking at is catenation. Don't worry, you get to understand each one of these. Then we also look at what we call hybridization. Okay, so it is because carbon can undergo, or carbon possesses these three properties. Okay, that is what makes it special. All right, that's we're now studying its compounds, as an entire field in chemistry. It's actually a different field in chemistry. I mean, there are professors or doctors that actually just specialize in this branch of chemistry. I mean, that is everything get to study at advanced level. Maybe when they are doing their masters or PhD, that's what they're going to have to do research about all through. All right. So hybridization, excitation, catenation. So we're going to be looking at each one of them to see what all these actually mean. All right. So we call that okay, these unique properties, we call them the unique properties of carbon. Okay, so before we begin to explain what each one of them means, we should briefly talk about the the makeup, the atomic makeup of carbon. All right, so you would recall that you recall from your from your periodic table, okay, periodic table of the elements, you'll recall that carbon is a group 4 element. Okay, you should have done that from. If you don't know that, you can revise atomic structure and periodicity and all of that. Okay, so you will recall that carbon as an element has atomic number. Its atomic number is 6. Okay, which means its electronic configuration, if you want to write it, that means it has in its first shell, all right, which is the what do you call it now? Is it the K shell? Okay, in its K shell, it has 2 elements, and in its L shell, 2 electrons, and in its L shell, it has 4 electrons. Okay, so say based on this, we can see it has its electrons are distributed in 2 shells. Okay, well, which also corresponds to it being on the period 2. Okay, so carbon is on period 2 in the periodic table, and then it is also in group 4, which the group usually corresponds to the number of valence electrons, that is unpaired electrons. Okay, so we're going to see all of that as we proceed. So it is actually in group 4 period 2. Okay, so you get to see why we're doing all of this now as we proceed. Okay, so this is its electronic configuration. If you are doing it in terms of the shell, that is how many electrons are contained in each shell rather. All right, so now if you go down to the orbital level, want to write the electronic configuration in terms of the orbitals, I think you should still remember the different laws when we talk about Pauli's exclusion principle and all of that. You can revise atomic structure if you still don't get what it is. So for its electronic configuration in terms of the orbitals, we have 1s, we have 2s, and 2p. So we know that the s orbital can only take 2 electrons. It can take maximum of 2 electrons. So this is going to be 2. So I have 2 electrons already filled. I have to fill in terms of increasing energy level. All right. So the next one is going to also take 2 electrons, being an s orbital. Then the next one is going to take, we have 4 electrons already filled. So out of the 6 electrons in carbon, so the only electrons left we occupy the 2p orbital. So we are going to have that way, 1s2, 2s2, 2p2. So this is its electronic configuration in terms of the orbitals or energy levels. All right, so this is electronic configuration of carbon, and again we can actually show this using the we can actually draw this out. Okay, we can produce an illustration of the orbitals. So we know 1s orbital. For s orbital, there is only one degenerate orbital. If you don't know what I mean by that, you should revise atomic structure. So the 2 elements, the 2 electrons are right there. Then in the case of 2s, it's an s orbital, so it has only one degenerate orbital. Only one degenerate orbital. So because of that, you have just 2 electrons in there. Then for the p orbitals, this would usually have 3 degenerate orbitals. So you have something like this. So these are the degenerate orbitals. 1, 2, 3. Alright, now so we're going to fill singly first before pairing, as we know. So there are just 2 electrons to be filled. So I have this and I have this. So I cannot pair them. I have to fill singly first because they have the same energy level. Alright. Unlike what we have here, where this one is at a lower energy level compared to this. So this has to be filled fully first before this one. Right. Just the same way, this has to be filled fully first before this one. Alright. So that is from atomic structure. Okay, so you can still remember all of that. Alright, again, you can decide to actually name. We know this is a p orbital and these are p suborbitals. So for instance, you can decide to name this, let's say 2px. That's just to tell you that this first suborbital is x, this one is y, and this one is z. Alright, okay, so we call this 2py and this 2pz. Okay, so that is that about that. So that's the electronic configuration, alright, of carbon. And this is the electronic configuration: 1s2, 2s2, 2p2, and this is the energy level diagram for carbon. Okay, for carbon element. Alright, so we'll be making use of this energy level diagram to actually explain these different properties. I mean, these unique properties of carbon: excitation, catenation, hybridization. Alright, so we can now begin. Okay, so I hope you get this already. In case you still don't understand what this is or how we came about this, please revise atomic structure. Okay, so we now pick on these properties one after the other. So when you talk about excitation, what does it mean? Excitation, it means to be excited. Okay, so excitation means we have an electron in a situation where we have an electron jump from a lower energy orbital to a higher energy orbital. Alright, so we've talked about, I've mentioned it just now, that this is a lower energy orbital relative to this, and this is a lower energy orbital relative to this. Alright, so now when you talk about excitation, now it means that you have an electron, a station or a process where an electron jumps from a lower energy level to a higher energy level. Alright, so that it jumps, or it goes from a lower energy orbital to a higher energy orbital. Alright, so how does this take place in carbon? Okay, so we just draw the energy level. We just drew the energy level diagram now. So on a good day, normally we should have this for carbon, just like we produced just now. You should have this for 1s, the 1s orbital. We're going to have this, and for the 2s orbital, you should have this also, because it is s is just one degenerate orbital. So you have something like this. Then for the 2p, okay, because it has 3 degenerate orbitals, you're going to have something like this. Okay, we produced that in the previous page, so it's still the same thing. So when you have it like this, this is the normal way it should be. So when you have it like this, we call this the ground state. Ground state. That is when each of the electrons is in its normal position. Okay, nothing has taken place here. This is the normal arrangement. This is the normal way the electrons should be positioned. Alright, so when you talk about excitation, it means you have an electron in a lower energy level or lower energy orbital jump to a higher energy orbital. All right, so in this case for carbon, you're going to have this um, electron or an electron, one of the electrons in the 2s orbital jump into the 2pz suborbital. From what we've done before, this is x, this is y, this is z. So this is 2px suborbital, this is 2py suborbital, and this is 2pz suborbital, or say orbital. Yeah, you call it. All right, so when it undergoes excitation, you're going to have a situation like this. For the carbon in its excited states, you're going to have this and this. Then you're going to have for this, instead of it being two electrons, one of the electrons has actually jumped, okay, into the 2pz suborbital or orbital. So you're going to have this right here. So I have this is here, this is here, and now this is here. So one of these electrons are actually jumped in the air. All right, so when you have a situation like this, we say this is its excited states. Like electrons in you have the electron on you, so it has decided to actually jump. It is jumping, so it's jumped from this point, from this orbital into this orbital. So that's what I mean by excitation. Okay, process whereby an electron jumps from a lower energy orbital to a higher energy orbital. So that is excitation. It is excited. I do. Okay, so you can have carbon undergo this what do you call it now? This process. Okay, carbon can undergo excitation. That's one of the unique properties of carbon. Okay, that is not to say that no other element can undergo excitation. Okay, so we're just saying this can undergo excitation amongst other properties it has, and this is one of the properties that make it suitable to form varying compounds, okay, which we now have to study separately, which we now devote one aspect, a whole aspect of chemistry to. All right, so that's what we mean by unique properties in this context. Okay, so now we can actually produce the shell diagram to see what we're talking about. Right, that means now this is the K shell. In this case, now this is the K shell. Alright, so that means in the ground state, you're going to have the shell diagram, so to speak. We're going to have it to be something like this. In the first shell, you have two electrons. So this electron and this electron. That's this number here, this number that actually precedes the SP whatever, actually tell us the shell number we are dealing with. Okay, so when you have 1 here, it means you are dealing with the first shell. 2 means you are dealing with the second shell. 2 means you are dealing with the second shell. All right, so they are actually in pairs like this. Okay, so on the outer shell, okay, this is how they are in pair here, because they can only be 2 here, so they are actually paired, right? So on the second shell, for instance, you're going to have something like this. So on the second shell, look at it, in the 2s in the 2s orbital, you have 2 electrons, so they're going to appear as a pair. Okay, so you have something like this. Say you have this, that's the pair. Then on the 2p on the 2p orbital, you have these 2 electrons. They are not paired, they are actually separate. So you can have something like this. This electron is here and this one is here. They are not together. So you can have this as the shell diagram for carbon in its ground states. Okay, so for carbon in its excited state, now look at what we have here. Okay, so in its excited state, you're going to have something like this. The first shell still has this two electrons paired, so we have them the way they are, just the way they are here. Then the second shell, we're going to have this. Now all the four electrons are separated. There is no paired electron, okay, in the first shell. So you're going to have something like this. We're going to have this palm. We're going to have this palm. You're going to have this palm. Okay, so basically what this should tell you, or what you can actually what should come to your brain when you see something like this, is the fact that now, unlike what we had here, okay, this can actually go into its octet state by actually pairing. So you can pair up this, you can pair up this, you can pair up this, you can pair up this. So you can pair up four different electrons. So that tells you it can actually undergo covalent bonding. In this case, if it's to undergo electrovalent bonding, I believe you know what I mean by electrovalent bonding. If you don't know what I mean by electrovalent bonding, please revise the topic, chemical bonding. Okay, so in this case, if it were to undergo electrovalent bonding, it means it would have to lose 4 electrons, or gain 4 electrons, to become octet, or to become stable, or to attain its octet state. Now that is going to require a lot of energy. It's going to require a lot of energy to lose 4 electrons or gain 4 electrons. Okay, so that is why carbon would usually form compounds via covalent bonding. So, and that will happen by pairing up this, pairing up this, pairing up this, and pairing up this. So that means for a given carbon atom, okay, it can form it will become stable when it has formed 4 bonds, that is 4 covalent bonds. So when you have it actually attached to 4 elements, okay, you're going to have it complete. So basically, in organic compounds, when it is stable, when the organic compound is stable or saturated, we get to look at that later. You're going to have the carbon element actually forming 4 bonds. So when it has 4 bonds, okay, it may not be in this form, but basically when it has 4 bonds, you say that it is actually stable. Okay, so to speak, can actually form compound. It can actually form compound when it already has also, or when you have up to 4 bonds, okay, surrounding the carbon elements, or each of the carbon elements. So you can have something like this. This can be double, then you have this single. So it is still complete like this. Can form you can have a compound where you can have this in a even organic compound. Okay, so it will usually have 4 bonds that way. All right, so this is what we mean by excitation. All right, so that is the difference between excited states and ground states. So that is that about that. One of the unique properties of carbon, excitation. So that is what we mean by excitation. Then we'll take on the next one, which we call catenation. All right, so we're done with excitation right here. So you know the implication of that now. Okay, so in the case of catenation, we say catenation is the ability of an element to form multiple bonds among itself, to form a long chain. That means carbon can actually form multiple bonds with itself to actually form a long chain. That's what I mean by catenation. Okay, so the chain could actually be a straight line, it could be branched, it could be straight. So we'll say now it is worthy of note here that carbon is the only element that actually exhibits or demonstrates this property. Alright, so carbon can actually form multiple bonds with itself. So you can have something like this: carbon, 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 carbon. Of course, to actually complete the whole thing, you're going to have this, of course. So it can actually form a very long chain with itself. So you can have a very, very long chain. Okay, so an example of this is a compound called can I remember this? Buckyball. Okay, or some call it Buckminster Fullerene. Can I remember this spelling? Buckminster Fullerene. I'm not sure this spelling is correct. Okay, I mean this one. Okay, so it's called Bucky Paul informally, and it is actually C60. That is, you have carbon forming a long chain. 60 carbon elements or carbon atoms forming a very long chain with itself, okay, or with themselves. Okay, so that is what I mean by catenation, the ability of an element to form multiple bonds, okay, among itself. That is, you have an element, it's atoms, several atoms come together, they form multiple bonds, okay, with themselves. Okay, so that's what I mean by catenation, and polycarbon exhibits this property as we've talked about now. Okay, so that is that about that. So you can form different bonds with itself. You can form single bond, you can form double bond, you can form triple bond, and so on and so forth. The bond can be straight or branched. All right, so that is what we mean by catenation. All right. Okay, so that is that about that. Then the next one, which we're going to take quite some time studying, is hybridization. So when you talk about hybridization, what do we mean by hybridization? So in the case of hybridization, we say that this is the mixing or blending of orbitals to form some set of new identical orbitals called hybrid orbitals. Okay, don't cram that. You don't need to cram that. We're saying that when you have orbitals, of course these are orbitals, this orbital, this 1s orbital, this 2s orbital, this is 2px orbital, this is 2py orbital, this is 2pz orbital. Okay, so we can have them actually mixing or blending. This you can have, for instance, this one mixing with this, or blending with either 3 of these, or just 2 of these, or just 1 of these. Okay, I mean, you can have this 2s orbital blending with 2px orbital, for instance. You can blend with 2px and 2py orbital. You can blend with the 3 of them. Okay, so when that happens, we say what has taken place is hybridization. That means a hybrid has been formed. Hybrid is an English word which usually denotes a combination, like you're actually combining two properties, or you're combining two substances, or you're combining two components. Okay, all right. It isn't necessarily two, mostly two. Anyways, okay, you can have I'm not sure, but it is mostly two. Okay, so hybridization means in the case of chemistry now, it means you're forming hybrid orbitals. So two or more orbitals actually mix or blend to form hybrid orbitals. So when that happens, we call that process hybridization. Right, so that is that about that. So we look at what we mean by this in details now. So look at what I just said. I said you can have 2s orbital blend with the 3 orbitals here. That is, it can blend with or mix with 2px orbital, 2py orbital, and 2pz orbital to form a hybrid orbital. Okay, you can also blend with only 2 of them. It can blend with just 2px and 2py. It can blend with just 2px. That's only one of them. All right, so that tells you that in the case of in this case, we can have carbon undergo 3 different kinds of hybridization. Okay, it can undergo what we call the sp3 hybridization. So carbon can undergo sp3 hybridization, it can undergo sp2 hybridization, it can undergo sp hybridization, or say sp1 sp hybridization. All right, so Look at it. There's no magic here. It's something quite straightforward. sp3 means you have the 2s orbital blend with the 3p suborbitals, so to speak. That's 2s orbital blends with 2px, 2py, and 2pz. Okay, they all come together to form a new hybrid orbital. Okay, then in the case of sp2, that means you have the 2s blend with 2px and 2py only, so they come together and form a hybrid orbital. We look at the orbital diagram shortly. So in the case of sp, you have just 2s and 2px coming together to form a hybrid orbital. All right, so that is that about that. So look at it now. So when you talk about, we now pick them one after the other. So firstly, we talk about the sp3 hybridization. So in the case of sp3 hybridization, what is it going to look like? We just said it now that it means the 2s orbital will blend with the 2p suborbitals, that's the 2px orbital, 2py orbital, and 2pz orbital. Alright, so what is that going to look like? So let's produce that together. What is it going to look like? What is the sp3 hybridized orbital going to look like? Alright, so that means you will have something like this. You know, on a good day before hybridization, okay, on a good day you have something like this. Okay, when the carbon is in its excited states. Okay, you know, we're dealing with the excited states now. Okay, so for the carbon in its excited state, you know, without hybridization, on a good day without hybridization, you're going to have this for the 2s suborbital. Then you're going to have for the this is going to be for the 1s suborbital. Then for the others, you're going to have this is the 2s suborbital. Then for 2s orbital, then you're going to have the 2px, 2py, and 2pz. Okay, so they are all together in the same orbital. We are like this. So you have this, you have this, and you have this. Okay, so this is the normal state before hybridization. Of course, the normal state in this context is the excited state. Okay, so this is the arrangement before hybridization. Of course, you can actually separate them into shells. This is going to be the K shell, of course, from what we've done before. This is everything here. This is the first shell, the K shell. All right, you know what this means now. K, this is L shell, this is the next one is M shell, and so on and so forth for other elements. Okay, for this now, for these two, this is actually the L shell. Everything here is in the L shell, as you have seen it here previously. Okay, so this is what it is. Okay, this is what it looks like before hybridization. Before hybridization happens, everything is going to be like this. Now, when hybridization happens, don't forget that we define hybridization. We said it is the mixing or blending of orbitals to form a new set of orbitals, which we call the hybrid orbitals. All right, so what is this going to be like for sp3 hybridization? It means that these 2s orbital will blend with this 2p orbitals. All right, so when that happens, of course nothing happens to this, so it remains the way it is here. So we're going to have something like this. When hybridization happens, we're going to have something like this. Then instead of this now being alone, it's now blends with these three. So you're going to have a hybrid orbital, okay, containing now 4 suborbitals. So you have something like this, this. So everything is now together. So we have this, and this, right? So obviously this is 2s, this is your 2px, this is your 2py, this is your 2pz. So it has blended, or it has mixed with this. Alright, so we call this the sp3 hybrid orbitals. sp3 hybrid orbitals. Alright, so these are the hybrid orbitals. So they are blended or mixed. Okay, and this is what happens after hybridization. This is what obtains after hybridization. Right, so that is that about sp3 hybridization. So what is the implication of all this? What is the implication of all this? So this actually gives or leads to some properties for a compound. That is, for a compound where the carbon atoms or some carbon atoms are actually sp3 hybridized, okay, so to speak. You're going to have some properties. Okay, that means from these properties you can actually tell for a given compound, or if a given compound, or if a given organic compound is sp3 hybridized, or sp2 hybridized, or sp hybridized, or a combination of two or three of these hybridizations. Okay, so we look at those properties now. As we have seen, okay, the number one property of sp3 hybridization, as we have seen, is that it actually requires the blending of one s orbital and 3p orbitals. Okay, so you can see that obviously that's what we mean by sp3, one s orbital and 3p orbitals. That's number one. Another thing is it leads to the formation of 4 hybrid orbitals. Obviously these are the hybrid orbitals, 1, 2, 3, 4. So it leads to the formation of 4 hybrid orbitals. That's quite straightforward. Another thing is it leads to the formation of saturated organic molecules. Okay, saturated organic molecules. So what you mean by saturated organic molecules? Let me tell you in layman terms. Now we'll get to see it later. What we mean by saturated organic molecule is in the sense that for the carbon atoms, all the bonds attached to the carbon atom is or the bonds attached to all the carbon atoms, or the particular carbon atom in question, are single bonds. So this is not a saturated organic compound if you have this in an organic compound. So you can only have it saturated when you have something like this. Okay, that means a particular carbon atom has 4 single bonds attached to it. Okay, so whenever you have that, the particular carbon atom in question is sp3 hybridized carbon atom. Okay, so that's how to note an sp3 hybridized atom. An sp3 hybridized carbon atom has only single bonds attached to it. So sp3 hybridization leads to the formation of saturated organic molecules. Okay, so that's what I mean by saturated. It means there are no double bonds involved in the compound. So a saturated compound means there is no double carbon to carbon, sorry, to be very specific, carbon to carbon bonds. Okay, that means a compound, an organic compound, is said to be saturated when all the carbon to carbon bonds, they are single bonds. Okay, so that is that about that. Carbon to carbon, don't forget. Alright, so sp3 hybridization leads to the formation of carbon to carbon single bonds. Okay, that's the implication. That is another way of that is why it leads to that's why we say it leads to the formation of saturated compounds. The compounds are so called saturated because all the carbon to carbon bonds therein are single bonds. Okay, so I hope you got that. Okay, so it leads to the formation of carbon to carbon single bond. That's another property we just mentioned. Then it's leads to the formation of a molecule which is tetrahedral in shape. Okay, this is what I mean by tetrahedral. It means that some, what's it now? its shape in space when you observe it. When you observe the molecules under some special apparatuses is tetrahedra, and maybe you don't need to worry about this for now, but it's good if you know it. But tetrahedra means you have something like this. For instance, when you have methane, for instance, we talk about all of these, you get to know why this is methane as we proceed in this discussion. You're going to have something that looks like this. Its shape is something that looks like this. Is a 3D diagram. You have something like this. So the hydrogen is going to be like this. You have another hydrogen right here. You have another hydrogen right here. You have hydrogen. Then here you have another one, hydrogen. Okay. Such that the angle, this angle, for instance, is 109.5 degree. Okay, so this is what I mean by a tetrahedral shape. How can I illustrate this for you? It's a 3D shape. This is a 3D diagram. You know, we are limited by space, so we're drawing it on a two-dimensional. This is just two-dimensional. On a two-dimensional plane or two-dimensional surface. Okay. Look at this. We're trying to say that we have something that looks like this. You know, imagine that you have this carbon at the center. Let's say this is the carbon. Then you have. See, can you even view this properly? And let's say you have this carbon here at the center. This is carbon. Then you have hydrogen here, and it happens that you have also something like this. You have another, hydrogen at this end. Then again, you have another thing. What can I use for illustration? Maybe you have another one like this. You have another hydrogen here. You have another one like this. You have another hydrogen here. So that's what I mean by a tetrahedral shape. And when you put all those four together, you're going to form that tetrahedral shape. Then the angle between those bonds is what I mean by this 180 degrees. Okay, so that's how they're going to be positioned in space. Okay, so that's what we are trying to draw here. Okay, so this will be by tetrahedral shape. Okay, so sp3 hybridization leads to the formation of molecules that are tetrahedral in shape, or a molecule that is tetrahedral in shape. All right, and then it leads to the formation of a molecule with bond length of 1.5 Armstrong. Okay, what we mean by that is this: if you have now, this is just to tell you the special the special shape or orientation of the different elements attached to the carbon atom. Okay, if you want to for instance, if you look at another compound that contains sp3 hybridized carbon atoms, you're going to have for instance, look at this other compound. This is propane. You're going to have this. You're going to have this. These are carbon hydrogen atoms, okay, attached to this. You have hydrogen, 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 hydrogen. So we're saying, so when you talk about bond length, okay, that means we're talking about basically what the actual distance, or the actual distance between this carbon atom here and this other carbon atom here. So we're saying that distance is very small. It is 1.5 Armstrong. Okay. What is Armstrong again? You can find out. I think it's 10 raised to power minus 11. Okay, you can ascertain that. So when you talk about 1.5 Armstrong, it's talking about 1.5 times 10 raised to power minus 11 meter. Okay, so something very small. The distance is very, very small. You cannot notice it with your naked eyes or with ordinary eye. That is why special apparatuses are used to actually visualize or measure all these, or measure all of these things, all of these parameters. Okay, so it leads to the formation of a compound, which is it leads to the formation of sp3 hybridization leads to the formation of a molecule which is tetrahedral in shape. Okay, that's one property. It also leads to the formation of a compound with bond length of 1.5 Armstrong and bond angle of 109.5 degrees. Okay, so you can also call it this bond angle. Okay, it is also 109 degrees and 28 minutes. Okay, so that's about that. It is approximately 109.5 degrees. All right, so it's actually 109 degrees and 28 minutes. Okay, so that is the bond angle. This is the bond length. The bond length is 1.5 Armstrong. The bond angle is 109 degrees 28 minutes. Okay, and the shape of its molecule is tetrahedral. Hope you know what I mean by that. I mean the spelling, tetrahedral in shape. Okay, so that is that about that. Then lastly, we just talked about the compound, the properties of sp3 hybridized carbon atoms or an sp3 hybridized carbon compound. Okay, it is found in alkanes. Okay, classification of organic compounds. We get to see that as we proceed in this topic. But generally, when you hear alkanes, it means compounds where you have hydrocarbons where you have carbon to carbon single bonds only, right? So these are alkanes actually. Okay, basically that should actually follow from all the other properties we have mentioned. The fact that when you have sp3 hybridization, you are going to have only carbon to carbon carbon to carbon single bonds. All right, so that is what we mean by that. So when you have hydrocarbons that have carbon to carbon single bonds only, they are called alkanes. So we say that they are found in alkanes. That is like another way of saying that they only form carbon to carbon single bonds. All right, so because alkanes are hydrocarbons with carbon to carbon single bonds only. All right, so that is that. So they are found in alkanes and their derivatives. Okay, we get to talk about the derivatives or derivatives. Is it derivatives or derivatives? Derivatives or derivatives, whatever. Derivatives of alkanes. An example of a derivative of alkane is something like dimethylheptane, 3-iodooctane, blah blah blah. Basically compounds where you have carbon to carbon single bonds. Okay, sp3 hybridization or hybridized carbon atoms are found in carbon to carbon single bond compound. That is compound that contain only carbon to carbon single bonds. That is, they do not contain carbon to carbon double bonds or triple bonds or whatever at all. They only contain carbon to carbon single bonds. Okay, so that's that about that. Okay, so that is that about sp3 hybridization. So the next on our list is sp2 hybridization. All right, so basically you know what it's gonna look like when you know what the orbital diagram is gonna be look like when the electrons are in their excited states. Okay, that's why we started there. That's before hybridization. Okay, it's the same thing for all of them before hybridization. Now sp2 hybridization simply means that you have one s orbital, okay, blending with two p orbitals, okay, and those are the two px and two py orbitals. All right, so what is going to happen? What is going to be formed after hybridization? That is when the hybridization occurs. What happens? So what will the sp2 hybrid orbitals look like? Okay, so let's quickly deal with that. So you have something like this. You're going to have something like this. The 1s orbital remains unaffected, so you have this as the 1s orbital on the K shell. So this remains like that on the K shell. Then on this other one, you're going to have the 2s orbital. This is the 1s orbital. So the 2s orbital is now blending with the 2px and 2py orbitals. So here I have the 2s, here I have the 2px, and here I have the 2py orbital, meaning that the 2pz orbital will now stand alone. This is 2pz orbital. So I have here one electron, one electron, one electron, one electron, of course as expected for excited carbon atom. Okay, now so this is the L shell, okay, for this now. So this is after you have your sp2 hybridization. Alright, so this has undergone sp2 hybridization. Okay, so this is what? This is the hybrid. This is the hybrid orbital. Alright, I'll say the hybrid orbitals. Okay, so what we have here is the sp2 hybrid orbitals. Hybrid orbitals. Okay, so this is the sp2 hybrid orbitals. You have combined the 2s and 2 of the 2p orbitals or suborbitals. Alright, so when this happens, we say we have sp2 hybridization. sp2 hybridization. Right, so that means the 2pz orbital is unhybridized. That means it has not been blended with or mixed with another orbital. It now stays alone. So this is the unhybridized. So this one is unhybridized electron. These are the hybridized or the hybrid electrons or hybrid orbitals. This is the unhybridized orbital. Alright, so that is that about that. Alright, so what does this mean? Okay, basically you already know what sp2 hybridization means. Now sp2 hybridization is a blending or mixing of one s orbital with 2p orbitals. Alright, so that is that about that. So in excited carbon atom, sp2 hybridization takes place when your 2s orbital blends with 2px and 2py orbitals. Alright, so that is that about that. So what is the implication of all of this? Okay, or what are going to be the properties of compounds with sp2 hybridized carbon atoms? Okay, so these are the properties of sp2 hybridization. Some will apply to the atom, some will apply to the compound they form. Alright, so we say number one is that of course from the definition it requires the blending or mixing of one s orbital and 2p orbitals. Okay, it requires the blending of one s orbital. You know what I mean by one is used here in the context of counting. Okay, it requires the blending of one s orbital. Okay, and we are not referring to like one figure like one s like a shell orbital. Okay, that will mean one s orbital, that is one of the s orbitals, and 2p orbitals. Okay, so that's one of the properties of sp2 hybridization. Then it also, we say that it leads to the formation of 3 hybrid orbitals. Unlike the sp3 hybridization, which leads to the formation of which leads to the formation of 4 hybrid orbitals. This obviously, quite obviously, it leads to the formation of 3 hybrid orbitals. And another thing is it leads to the formation of unsaturated organic molecules. Unsaturated organic molecules. So it leads to the formation of unsaturated organic molecules because there is an unhybridized orbital presence. Because of the presence of this unhybridized orbital, okay, the organic compound it forms, and the organic compound formed by sp2 hybridized carbon atoms are going to be unsaturated because there is still one left which is unhybridized. Okay, and how you will know that is because there is going to be typically how you will know that in an organic formula. When you have it's in an organic compound, when you have its structural formula is that you are going to have a carbon to carbon double bond. Okay, so the double bond tells you that that double bond can actually be reduced to a single bond by having the one of the elements actually attached, or the element separately attached to one other electron each. Okay, so that is why we say it is actually an unsaturated compound. Unsaturated in the sense that there is one unhybridized carbon orbital. Okay, unlike what obtains in the sp3 hybridization, where there is no unhybridized carbon orbital, and hence all the bonds are carbon to carbon single bonds. In this case, because there's an unhybridized carbon atom, that is taken care of by having a carbon to carbon double bond. Okay, so it leads to the formation of unsaturated organic molecules due to the presence of one unhybridized electron. Okay, so that is that, or one unhybridized orbital. Okay, all right. So another thing is it leads to the formation of carbon to carbon double bond. So whenever you see carbon to carbon double bond, it means the carbon elements or the carbon atoms involved are sp2 hybridized, so carbon to carbon double bond. So whenever you see a compound where there is existence of carbon to carbon double bond, it means the compound contains sp2 hybridized carbon atoms. Okay, and the specific ones that are sp2 hybridized are those carbon atoms having the double bond. Okay, so that is that about that. All right, another thing which is one of the properties of this hybridization is that it leads to the formation of a molecule which is planar in shape. Just unlike what we had in the sp3 hybridization, where the compound or the molecule is tetrahedral in shape. I hope you can still remember that. In the case of sp2 hybridization, the molecule is planar in shape. How do we mean, or what do we mean by that? Look at this compound where we have something like, look at some, what do you call this now? Ethene. Okay, look at ethene. C2H4, for instance. Okay, this is its structure. It actually has carbon to carbon double bond. Okay, so the structure is like this. Okay, you have something like this: carbon to carbon double bond, sp2 hybridized carbon atoms. Then you have hydrogen attached to this, hydrogen attached to this, hydrogen attached to this, and hydrogen attached to this. So that's a planar shape. That means you can actually have them drawn, the way they actually are, the way they actually appear in a plane like this. It is a planar shape. Planar. This is what I mean by planar, not planar. It is actually planar. That means it can be they actually can be shown in a plane. This is a plane now. This book is a plane, a surface, two-dimensional surface. What I mean by a plane, right? All right. So that's a planar shape, and this is what it looks like. All right. So it leads to the formation of a molecule with a planar shape, or which is planar in shape. Unlike sp3 hybridization, where the shape of the molecule is tetrahedral, three-dimensional, right? So another thing is it leads to the formation of a molecule with bond length of 1.4 Armstrong. Okay, that tells you that the distance between this carbon atom and this carbon atom is 1.4 Armstrong. That's 1.4 times 10 to the power minus 11 meters. Okay, that is that about that. And the bond angle is 120 degrees. Okay, that's the bond angle. Like this angle here is 120 degrees. Okay, so the bond length is 1.4 Armstrong. The bond angle is 120 degrees. Okay, unlike what we had In the case of sp3 hybridization, where the bond angle was 109 degrees 28 minutes, or approximately 109.5 degrees. All right. Sorry, 108. Why am I using 109 like this? Happy. It's 108. Oh, please. Sorry, it is 109. Can you imagine? Now, wow. Okay, 109 degrees 28 minutes. That was for sp3. In the case of sp2, we can see here the bond angle is what is it now? The bond angle is 120 degrees and the bond length is 1.4 Armstrong. Alright, so that is that about that. Then it is lastly one of the properties of sp2 hybridization. It is found in alkenes. Basically, that is like we are restating the fact that it leads to carbon double bonds. Okay, it is found in alkenes and their derivatives. Alkenes and their derivatives are those compounds or organic compounds that contain carbon to carbon double bonds. All right, so basically we're saying the same thing. All right, so whenever you have wherever you have carbon to carbon double bonds, you have sp2 hybridization or sp2 hybridized carbon atoms present. All right, so that is that about that. Okay, that is all for now about sp2 hybridization. So we talk about the next kind of hybridization, and the next kind of hybridization is sp hybridization. So you know what this is going to be like already. You know what to expect from this already. So that means in the case of sp hybridization, you have the blending or mixing of one s orbital with one p orbital. That's one for the s orbitals, one s orbital and one p orbital. All right, so you have them blend or mix. Okay, and when that happens, you're going to have a hybridized orbital, which you're going to have two hybridized orbitals. Okay, unlike sp2 where you have three hybridized orbitals, and sp3 where you have three hybridized orbitals. All right, so what is this going to look like, and what is going to be, or what are going to be the attendance characteristics, okay, or properties of sp hybridization? So as you should expect for an excited carbon atom, you're going to have, when it undergoes sp hybridization, because now you have just one s orbital and one p orbital, that means you're going to have the 2s orbital and the 2px orbital blend or mix together. Okay, that means you're going to have the 2py and 2pz orbitals unhybridized. Okay, so basically you're going to have two unhybridized carbon electrons, or two unhybridized orbitals. Okay, and of course that means the two unhybridized will tell you that two more bonds can actually be broken in the system. All right, just like when you add one unhybridized orbital here, implying in the real sense that you can actually have one other bond that may be broken in this system. All right, so that is that about that. Okay, so one more bond that may be broken. I mean, in terms of the carbon atom, you can have one more bond broken from the carbon atom. That is, instead of having double bond, you can have it become a single bond by some sort of reaction. Okay, so that everything will now be single bond. Okay, so what is this going to look like for the orbital diagram in the case of the carbon atom? So look at it. The 1s orbital remains unchanged because it is not undergoing the hybridization. So you have two electrons there as usual, 1s orbital. Then that is everything we have for the K shell. So this is everything for the K shell. In the case of the 2s now, so you have the 2s orbital now blending with the 2px orbital, only this and this, so that's why we call it sp. One s orbital and one p orbital, so one electron, of course, with carbon in its excited state. So you have this 2p and 2pz still together. So you have 2py and 2pz still together. So you have one electron here, one electron here. So what has happened here is that what this has been sp hybridized. Okay. So this is what the sp hybridized or sp hybrid orbitals. So these are the sp hybrid orbitals. All right. So that is what we mean by sp hybridization. You have one s orbital mixing or blending with one p orbital. Okay, and that gives you the sp. Is sp or not sp2? The sp hybrid orbitals. All right. So that is that about that. That is what it looks like after hybridization. All right. So what are the properties of sp hybridized carbon compounds or the sp hybridized carbon atom? All right, so we look at that one after the other. So that means the carbon atom, sorry, in the carbon atom, the two electrons that are unhybridized, I mean this and this, can actually undergo further reactions. Okay, just like this one electron that is unhybridized can undergo further reaction to break the double bond. Okay, so basically you expect that there is going to be triple bond here, such that you have two bonds that can actually be broken by having these unhybridized electrons undergo some reaction. All right, so just see it in that sense for now. When you get into the university, you're going to learn appropriately what this is, especially if you are dealing with chemistry or chemical engineering or anything related. Okay, you're going to learn all of these things in details, but just know these basic things about them for now. All right. So one of the properties of sp hybridization is that it requires the blending of one s orbital and one p orbital. You can see that already. One s orbital, which is the 2s orbital, and one p orbital, which is the 2px orbital. All right, they come together to form the sp hybrid orbitals, leaving 2py orbital and 2pz orbital unhybridized, which means you have two unhybridized electrons. All right. Another property is that it leads to the formation of two hybrid orbitals. We already saw that. It leads to the formation of unsaturated organic molecules with a very high degree of unsaturation. Okay, due to the presence of two unhybridized electrons. Okay, we saw initially or earlier that this one leads to the formation of unsaturated organic compound. Okay, due to the presence of one unhybridized electron or one unhybridized orbital, if you like. So in this case, this one has two unhybridized orbitals. That means the compound is going to be highly unsaturated, highly, to drive home the point that it is more unsaturated compared to compounds with sp2 hybridization. Okay, so that's what it means. So because in this case now you have two unhybridized or mixed or unblended carbon orbitals, all right, or carbon electrons. All right, so that is that about that. It leads to the formation of unsaturated organic molecules with a very high degree of unsaturation due to the presence of two unhybridized electrons. Okay, so that is that about that. Another thing, one of the other properties is that it leads to the formation of carbon to carbon triple bonds, expectedly carbon to carbon triple bonds. So you can have something like this, triple bonds, which tells you that you can actually break off two more bonds to make this single. So that is to saturate this. You can actually have these, attached to other elements so that this bond here will just become single bond. Okay, so that is what is meant by it being unsaturated. If you have noticed, these properties we are listening, just like a way, like you might tell this particular property is most likely another way of explaining another property we probably have mentioned before, all right, or just another way of explaining the whole thing happening here. Okay, so it leads to the formation of carbon to carbon triple bond. Okay, just like sp2 hybridization leads to the formation of carbon to carbon double bond. sp hybridization leads to the formation of carbon to carbon single bond. Okay, sp hybridization leads to the formation of carbon to carbon triple bonds. All right, so that's that about that. Then another thing is it leads to the formation of a molecule which is linear in shape. Okay, so compounds that contain sp hybridization or sp hybridized carbon atoms actually are linear in shape. For instance, look at ethine or ethine. Ethine is going to be like this. You're going to have something like this. You know, each carbon atom can only have 4 bonds. So you have 3 bonds already, or a triple bond with themselves. So this can only be like this and like this. So actually linear in shape, forming a straight line. You know, this is linear. This one is planar. The other one is tetrahedral. This one is one dimensional straight line. This one is 2 dimensional, and the other one is 3 dimensional. Right, so it's gonna form a molecule which is linear in shape. All right, so another property is it leads to the formation of a molecule with bond length of 1.33 Armstrong. So I mean that this one, the distance between this and this is 1.33 Armstrong. 1.33 Armstrong. All right, you can see that the bond length is decreasing. For sp3 it was 1.5 Armstrong. For this one it's 1.4 Armstrong. For this one it's 1.33 Armstrong, which tells you the more you know, when you go single, you're gonna be far apart. When the bond is double, it's like they're coming further close. Okay, they are coming closer together. The carbon atoms now, they're coming closer together. So the bond length is going to decrease here. They're coming further close together. The bond length is going to further decrease to 1.33 Armstrong. All right. So that is what it is. It is what it is. All right. It is what it is. Then the bond angle. Obviously, the bond angle is 180 degrees. That's like you have something like this straight line. Yeah, the angle between this and this 180 degrees, just like what we had here, 120 degrees. This one is 180 degrees. So that's the bond angle. So the bond length is 1.33 Armstrong and the bond angle is 180 degrees. So it is found in alkynes and their derivatives. Obviously, you should know that. That is another way to tell you that it is found in compounds with carbon to carbon triple bonds. Right. So when you have any compound that contains either 1 or 2 or 3 carbon to carbon triple bonds, we know that it contains, you know, sp hybridized carbon atom. So we see it is an sp hybridized compound. All right. So that is that about that. So example, you can have this ethine, you can have what we call hexine, you can have its derivatives or derivatives of the alkynes like 2, 3 dimethyl, but 2 ions. Okay, you get to learn about all of this naming when we get there. All right, so that's that about that. That is that about that. So I think we're done with hybridization. Now, if you listen carefully, if you follow this carefully, you would notice something, or you should know something by now, that you can have a compound that contains more than one, you know, more than one hybridization, so to speak. For instance, you can have a compound that contains carbon to carbon triple bonds as well as carbon to carbon single bonds. Okay, you can have a compound that contains carbon to carbon double bonds as well as carbon to carbon triple bonds. Okay, so that means, for instance, we can have a compound that contains both sp2 hybridized carbon atoms and sp3 hybridized carbon atoms. You can have a compound that contains both hybridized carbon atoms and sp2 carbon atoms, sp2 hybridized carbon atoms, and also sp3 hybridized carbon atoms. Okay, so an example, for instance, are the aromatic compounds. You get to know what we mean by that later on. What's it now? Aromatic compounds or aromatic compounds, compounds like benzene. Okay, they contain sp3 hybridized carbon atoms and sp2 hybridized carbon atoms. Okay, you have also in that category you have what we call the toluene. These ones contain both sp3 and sp2 hybridized carbon atoms. Why am I writing them like this? Everything is small. Sp3 and sp2 hybridized carbon atoms. Okay, they are found, both of them together, they are found in aromatic compounds like benzene, toluene, benzoic acid, okay, etc, etc. Right, so that is that about that. Okay, so that summarizes the three unique properties of carbon, okay, which makes it suitable for a special study, okay, which we have now termed organic chemistry. All right, so the study has been devoted to it because it contains some unique properties, and we have looked at what those unique properties are. We've looked at what we call excitation. We've looked at catenation, excitation, in that you can have one electron from a lower energy level jump to a state of higher energy level. All right, so carbon undergoes that or exhibits that property. And then you have, we've looked at catenation, which means the ability of an element to form multiple bonds with itself. All right, so we looked under that. We said we could have something like a Buckminster-Fullerene compound, which you call also the buckyball, okay, which has the formula C60. So we said that carbon was the only element that actually could undergo such that could actually exhibit such a property in that it could form multiple bonds with itself. All right, that's one of its unique properties. Then we also talked about hybridization, which are in three categories. You can have sp3 hybridization, you can have sp2 hybridization, you can have sp hybridization, and we already saw that sp3 hybridization would lead to the formation of carbon to carbon single bonds because there are no unhybridized carbon electrons or unhybridized orbitals in that case, as we have seen from the diagram so far. You can also have sp2 hybridization, which will lead to the formation, or which will be recognized by the formation of carbon to carbon double bonds, and which means the compound is going to be unsaturated. All right, and in the case of sp hybridization, it's going to lead to the formation of carbon to carbon triple bonds, which means the compound will be highly unsaturated. All right, so that is that about that. If you still don't get some part of this, you can revisit, you can revise to understand what you mean by that. Okay, so let's move to another category or another business under organic chemistry. Let's quickly introduce it before we end this class. So we'll proceed from there in the next class. It is about the formulas used in organic chemistry. Formulas or formulae used in organic chemistry. So this is everything about unique properties of carbon. So let's talk about formulas. Formulas used in organic chemistry. I was going to write organic chemistry. Organic chemistry. So we have different formulas we're going to use in organic chemistry. So there are four of them. We call one the empirical formula. Empirical formula. We're going to explain each one of them and how to derive them and all of that. Another one is the molecular formula. We're going to concern ourselves with the molecular formula. Another one is the structural formula. Structural formula. Then we have what we call the condensed formula. So what do these things mean? We're going to be talking about them one after the other. Alright, so when you talk about the empirical formula, that's the first one. We talk about empirical formula. In the case of empirical formula, we talk about, or we mean or imply, the formula that shows the simplest ratio of combination of the elements. So it shows the simplest That's the keyword there. The simplest ratio of combination of the elements. Okay, that is the empirical formula. All right, so look at it. This is what I mean by simplest. If you have a compound like let's say C3, you have something like this now. You have something like C3H6, or you have something like C2H6, or you have something like C2H2. Okay, look at all these. These are actual formulas, all right, of a compound. These are the molecular formula. I've said it already. You get to see that. Okay. When we talk about it, they are empirical formula. Empirical means the simplest ratio of combination of the elements, okay, in this compound. So what are the elements here? Carbon and hydrogen. So you have 3, okay, carbon atoms combined with 6 hydrogen atoms. So what is the simplest ratio of combination? Okay, so when you divide by the simplest, this is 1:2. All right, so that's the simplest ratio of combination. So the empirical formula for this compound is simply CH2, 1 of carbon to 2 of hydrogen. Okay, that is why 3 of carbon will need 6 of hydrogen. So that's what I mean by empirical formula. It shows the simplest ratio of combination. It is not the actual ratio of combination, it just shows the simplest ratio of combination. All right, so that's what I mean by empirical formula. So this is the empirical formula of this compound C3H6. Now for this compound, what's the simplest ratio of combination? Of course, we can divide all through by 2. So the simplest ratio of combination is shown by CH3. That's the simplest ratio of combination. That's the empirical formula for this one. Okay, so this is the empirical formula for this compound. So this is the empirical formula for this compound. All right, and for this one, the simplest ratio of combination will just be CH, 1 carbon, 1 hydrogen. So that's why 2 carbon will go with 2 hydrogen. So that's how to get the empirical formula of a compound, an organic compound in this context. All right, so that is that about that. It's quite straightforward to deal with. That's what I mean by empirical formula. Okay, so the molecular formula, that's the next thing. Okay, we're going to talk about structural formula. Okay, we're going to begin discussing structural formula from the next class. So what do you mean by molecular formula? So molecular formula shows the actual ratio of combination of the elements. All right, actual ratio of combination of the elements. So in the case of molecular formula, this is what you usually refer to. This is what we usually use when we're writing what's now chemical equations, and when we want to name organic compounds. We actually have to use their molecular formula. That's when we want to know the actual ratio of combination of the elements, okay, in each molecule of the substance. So that's the molecular formula. Empirical is to just tell us the simplest ratio of combination. All right, so there are calculations around this. For instance, if you are given some details about the components or the composition of a compound, how can you find out what its empirical formula is? How can you find out what its molecular formula is? And all of that. So that is where we're going to move on, or that's what we're going to take up in the next class. Thank you very much for your interest in Mark's tutorials. We continue from here in the next class. So please ensure you understand all this perfectly and go through your textbook, your new school chemistry, that's a biochemistry, and your Lambert's chemistry, and try to read all of these things again. If you see anything that contradicts or appears to contradict what I have explained so far, call my attention to it so that we can clarify it together. Okay, that's not about that. You'll see in the next class.